Hello everybody, I'm Robert Dwabeek, and together with my colleagues from Ford, we will give you today an insight in what we call model-based agility with FAST. FAST stands for Ford Automated System Simulation Toolchain, and we developed this full vehicle simulation environment to enable virtual development. And one of the goals we have is written down in the bottom, virtual vehicle built in minutes instead of months. But as I said, I'm not doing this alone. I will give an introduction about why and what is FAST. Then Raghu will take over and really shows the mechanics of the tool chain with how does it work. Then Stephen will take the next part and really will explain how we create full vehicle simulation out of the FAST environment. And then Nick will explain us how we scale it up to production. Nate will take the last section about the inner sourcing for model development. And at the end, I will give a short summary about the presentation. So let's get started with what is FAST and why do we need it. So let's start with a quote from Nancy Leverson. She's an expert in system and software safety. Software and digital systems provided tremendous power in building complex systems not previously possible. But increasing the power comes with a price. Large software systems are fiendishly difficult to get correct. The difficulty of building such a software is often underestimated by engineers. And I think we can say this is also valid to our automotive section, because I think modern vehicles are getting hundreds of millions of lines of code. And I think we can say automotive vehicles are extremely complex, mass-produced mechatronic systems. And that are the vehicles of today. But what about the future? We're coming into the automated driving field with much more complex vehicles. And it is for us key important with this rising complexity to detect system issues early on in development. And then from the technical point of view, a couple of years back we did a test from if we want to simulate an ADAS feature, what has to come together? And you can see here, it's a lot. And every department had different development methodologies. And the reasons are different, but they all had good reason to choose this development methodology. But to bring it all together in one simulation environment, it's really difficult to get it correct. To make a good simulation out of it, only with collaboration we can achieve this. Simulation inefficiency. At the same time, we asked the CAE engineer, where do you spend a majority of your time? And the triangle, what will show up in a minute, will show the amount of work he spends. So take the triangle, if the full triangle is 100% of his time. We asked him, where do you use majority of the time? And he's really spending a lot of time in tracing and collecting component models. Then he's building the virtual vehicle, he starts to debug, and then only the top of the iceberg is simulation. And he does some system debugging for simulation purpose. But that's not really efficient, so we should try to improve that. And that's what we try to achieve with FAST. So tracing and collecting component model is still the baseline. Building virtual vehicles should go faster. Some debugging has to be done. We are not perfect. Some things will go wrong. But then you really free up time for doing modeling and simulation fully integrated into car line development. And that's what we are trying to achieve. So what is FAST? It's a combination of modern software developing techniques and tools like GitHub and Git, together with the MATLAB simulating product and a smart cross-organizational team from Ford. And I think the cross-organizational one is the one to point out. We are all distributed in different departments inside the company, but collaborating. And Nate will give a little bit better view about that. And that is what comes together inside FAST. Today we have around 500 members, or we call passive users, 100 to 150 active users who are using it on a daily basis, and 30 members in the DevOps team. That doesn't mean these 30 members are full-time developers. They are users and they are developers. And Nate, in the inner sourcing section, will give a small insight into that part. So now a little bit what the FAST model is doing. So it starts with the vehicle control architecture. These are captured in our company quite early in the development in the DBC files. Then we add the bill of model, and Raghu in his section will explain in more detail what the bill of model is. But in general, it's a list of all the components that goes into the simulation. And then we build a skeleton/system model. This is just an empty framework with all the IOs being set up. It's done fully automatic. Then we have the skeleton system model, but we have to add some component models. We pull them from the GitHub cloud, and then the next section you will see how it works. And then we have vehicle models, different kind of vehicle models. Because there is no single virtual vehicle. It's like designing a vehicle. You start with some sketches on paper, then you go into CAD drawing, and then at the end you have a full product, fully with all the masses and all the details. And it's the same for this kind of modeling and simulation. You start with rough models, and Nate in the final section will show the approach we take there. And then you have to have a test plan. Of course, the DVM and DVPs with metrics, but also the explorative testing. How many issues did you discover by just turning on the ignition key in the real prototype? I would assume a lot. And that is what we call virtual development. That all being summarized on this slide. So the last equations are placed into this picture. So we start with the vehicle control architecture. Then we have a feature bill of models. We build the skeleton. We include the components from GitHub. And then you can do virtual development and verification. And that being said, now Raghu will give us an insight about how it works technically. So the mechanics of building a FAST model. Raghu?
Thanks, Robert. Hello, everyone. My name is Raghu Bhaskaran. Let's take a look at FAST ecosystem and the mechanics of building a FAST model. What do we need to build a FAST model? MATLAB Simulink is the main application in FAST ecosystem. All tools, models, and resources are version controlled in Git and shared through GitHub. An Excel-based model BOM is all you need to define the content of a FAST model. ECU architecture files are in vector DBC format, and ECU models are in MATLAB Simulink, and vehicle component models can be CarSim, CarMaker, Vehicle Dynamic Block Set, etc. Plant interface sheet contains the plant input-output data. But it all starts with Bill of Models. Bill of Models is an Excel document unique for each FAST model. It is categorized into several sections. It has a metadata section with program, feature, and variant name. It has a component section with a list of all ECU that you would need in your model build. All vehicle dynamics models are listed in the vehicle section, and the vector DBC file, the network architecture files are listed in the network section. Each line item has a GitHub location where the models are stored, and it also has an associated release attribute to it. This enables plug and play. There are several other sections that are needed for the model build. It's added in those sections. So how do we build a FAST model? We have a one-click solution to build a system model. FAST is an automation wrapper for several linked tools. It takes model BOM as input from GitHub Cloud and runs the tools in sequence to build the model. The CAD model builder builds the skeleton model from network DBC file. It is developed by MathWorks, Scott Furry, and team for Ford Motor Company. A GitHub repo browser pulls ECU content from cloud. It is developed by Nick Adams from Ford. And the plant interface builder takes in the plant interface sheets and the vehicle component models to build a full vehicle model. And finally, we have CAN connections that are then made through a script developed by John Broderick from Ford Motor Company. So FAST is an automation wrapper for several linked tools that builds the full system vehicle models from components in the GitHub Cloud. So let's take a quick demo of the end-to-end process. First, we fire up the FAST tab in MATLAB. And then we browse and select the model BOM and load the model BOM. And then click the FAST button to go through the end-to-end process. First, all the FAST tools are pulled, and CAN model builder then begins to build the skeleton model. The build process goes through one network at a time, and the ECUs in each network are connected. All this information comes from model BOM. Once all the ECUs are added, we have the gateway module connecting all the networks, and the skeleton model is built. The next step is to pull all the component models from GitHub onto the skeleton model that we just built. The GitHub repo browser does that job. Once that is done, we build the plant interface using the plant interface builder. Then we compile the model. And then we run the CAN connection scripts. Once we restart the virtual vehicle, we have a model ready for feature simulation. I hit the start button. The simulation begins. So let us quickly look at the anatomy of a FAST model. On the top left, you have, on the title block, you have the program and feature name. And then we have the virtual ECU breadboard for mill, sill, and hill ready. And on the top right corner, we have shortcut buttons to all FAST tools. And we have a placeholder for feature, driver, display, and vehicle model. So FAST generates an ECU framework that can accept plug-and-play components to capture as many use cases as possible. So Stephen Foster will now take you through in detail about the plant interface builder. Steve?
Thank you, Raghu. Hello, everyone. My name is Stephen Foster, and I'll walk you through creating full vehicle simulations within the FAST model by connecting the system components to the vehicle model. At Ford, we had the need for various vehicle dynamics models within the FAST environment. The choice of model will depend on various factors that include the required model fidelity, simulation speed, as some users require models that are real-time capable. Licensing costs and availability are also a factor. Experience of the user. Some users are not proficient in certain vehicle dynamics packages. And sometimes it simply comes down to the preference of the engineer or the department. The plant interface builder enables users to seamlessly connect or switch between any vehicle dynamics model used at Ford within the FAST environment. Some vehicle dynamics models used at Ford include the vehicle dynamics block set created by MathWorks, CarSim, IPG's CarMaker, MSC Adams, and internally developed Simulink models. This process allows users to share FAST models and easily switch between vehicle dynamics packages by leveraging the capability within the plant interface builder. The plant interface builder is the one-click solution for connecting vehicle dynamics models within the FAST environment. It all starts by detecting the signals needed within the component model. That is done automatically by the plant interface builder. These signals are then mapped to the appropriate vehicle dynamics package through the Ford Global Plant Signal Database, internally known as GPSDB. This database was created to solve the issue we had internally. That is, how do we automate these connections when signal names are not consistent within ECU models? The GPSDB database was the solution to this problem. The database contains the defined signal names and their appropriate mapping to all the vehicle dynamics packages at Ford. The interface builder then is able to generate the plant interface sheets needed for each ECU component model. The vehicle dynamics model selected in the interface builder GUI is then added to the FAST environment, and the connections between the component ECU model, driver, and vehicle are all done in a matter of seconds. Now the user is on their way to start simulating and exercising their model. It was touched on briefly in the previous slide, but what is a plant interface sheet? The plant interface sheet contains the mapping between the controller, GPSDB signal name, and the desired vehicle dynamics model. In this example, the MathWorks developed the vehicle dynamics block set, or VDBS. The steering controller in this example has an input signal, steer ang, with units in degrees. The signal coming into the plant receive block is the GPSDB signal, ang steer wheel position in radians. Based on the mapping defined in the interface sheet, the plant interface builder will generate the appropriate connections for this signal automatically, including the required gain blocks and signal naming. The same is done on the transit to plant side, where the steering controller passes column torque in Newton millimeters to GPSDB named torque, steering column assist in Newton meters. This is a simple example to show the basics behind the interface builder. I will now show a quick video of the interface builder in action. You can see out of the box, the plant receive and transmit come with default settings, so there's no mapping. The vehicle block as well comes in a default state with an empty vehicle model. Once we open the GUI, we have the ability to view and edit any of the plant IO sheets. So here we can see the brake plant IO sheet that's being used. And this contains all the mapping that's defined. With one click of a button, we can generate the vehicle model, in this case, VDBS, in a matter of seconds. There's a status bar at the bottom to show when it's complete. Now looking at the brake plant receive, we have the connections as well as the transmit side. The vehicle model now has the receive from controller connections, map, as well as the transmit side. We have a pass-through block that allows signals to be passed from one ECU to another. And then the vehicle block finally has the vehicle dynamics block set model included. Now I will pass you over to Nick Adams, who will discuss continuous integration.
Thanks, Stephen. My name is Nick Adams, and I'm going to talk about how we use continuous integration with the FAST process. We've seen in detail how the FAST tools work for one single system model. At Ford, of course, as Robert discussed previously, a single vehicle is made up of dozens of ECUs, so dozens of models, and each of those models is made up of many different fidelities of model and many different variants for each car line. All of those component ECUs, all of their variants, and all of their different fidelities are stored in GitHub. Each team is responsible for their own repository. For example, when the brakes team has their own model, they are designing it for each car line that they're interested in. So Mustang, F-150, etc. And every repository has as many variants as they think they need. So you can imagine then that we can automate most of this process using a continuous integration system like Jenkins. For example, we can collect all of the variants for each type of model, run both fast unit tests and unit tests that go along that were created by the developers of that model. And we can do that then for each and every variant. Just back of the envelope numbers here, if we're testing 10 or 15 car lines, each with an average of 30 ECUs, that's kind of the level of tests that we're running daily or nightly. Once we've tested all those, we store all of those, what we're calling component models, on what is a platform we've called Fast Garage. This allows us to view component models online from a browser, thanks to the MathWorks web view functionality. And so I'll show a brief video of a very simplified interface of the Fast Garage to kind of show how we help engineers discover the models and go through the different fidelities to see what they might need for their system model. So as I said, this is a simplified interface of the current models that we have within GitHub. And so each of these is a different repository owned by a different internal organization. And all of these are different branches or different tags in GitHub specifying different fidelities or different variants. We can look at a steering controller, power steering control module, and we can see that we can interact with this model sort of in a read-only view, the same way we would in MATLAB Simulink. We can see on the side there's parameters. We can go deeper into the model. We can control the same way that we would a normal model. We can zoom in, zoom out, pan around. We can go all the way down to the state flow. And so this has really allowed us to speed up letting users find models themselves, so no one has to go through and pull tons and tons of content down to their own computer. And this has been really great with the Simulink web viewer to just be able to export with Jenkins HTML versions of all of these models. And so now that we have all the components tested and discoverable, we can start creating models from the bill of models that users have created. So Raghu described this process, but now imagine there are, 50, 100 bill of models contained on GitHub, just each describing some use case. We can go through and in parallel generate all of those different use cases and create all of those different bill of models and instantiate them by piecing everything together in the way that Raghu described. So one of these pipelines can take anywhere from 10 minutes to an hour, especially if there are a lot of feature level tests that are really trying to validate implementation models. Those will always take the longest. So again, this is happening daily, often overnight, since people will check in all their code, and then at night we'll have everything go through what it needs to. But this ends up being dozens of bombs, all tested in parallel for a combined 40 plus hours each day. If you're curious how we make this happen, there's a lot of virtual machines, Kubernetes and Docker containers at play here to manage a lot of our tools only run in Windows. Some of them work better in Linux. Some of them can be done in the cloud. Some of them need to be done on hill stands. So there's a lot of different tools at play to make this happen. And now I will turn it over to Nate, who will describe the inner sourcing development process for FASST.
Thank you, Nick. My name is Nate Rolfus. I'm going to talk about how we ensure which models are the right models for each user simulation, or put more bluntly, and one of my favorite quotes, all models are wrong, but some models are useful. To answer this, we turn to a powerful development process that's been used for many years by the open source community. Inner source is the adoption of open source development within a large enterprise like Ford. The first tenet is collaboration. Let me ask you a question. How many times have you started a project from scratch only to find out that someone else has started something similar months or even years ago? It can be very frustrating for both parties, since one person says, "You're reinventing the wheel," and the other person says, "You should put your wheel where I could have found it." These types of collaborative disconnects can add up to huge costs and inefficiency. With inner sourcing, we can minimize disconnects and improve both efficiency and quality by always leveraging other people's work and brainpower to develop our projects. The second point is communication. One benefit of agile tools, such as GitHub, is everything becomes a searchable, self-documenting database. All of the bugs, enhancement requests, design decisions, and problem solving is preserved in the development workflow through issues lists, pull requests, and commit histories, rather than being buried deep in someone's email inbox. The third point is that everything we do has a basis in merit. Users are developers, and developers are users. If you have a really cool, new, and genius way to solve a problem or fix a bug, the project is yours to branch off and go solve it. If you succeed, your fix gets merged in, you get kudos, and PowerPoint engineering takes a backseat to really great problem solving. The last point is a quote from Eric Raymond, one of the pioneers of the open source development process. When describing what draws people to work on open source projects, he called it the plausible promise. What he meant is that you shouldn't necessarily start from an empty sheet of paper and ask people to start inner sourcing with you. Rather, you should start with what he called a plausible promise. That's something that may be crude, have some bugs, maybe only half finished, may not have much in the way of documentation, but it runs and it can convince people that if they start helping you out, it can become something really neat for everyone in the foreseeable future. Our plausible promise with FAST started with the month to minutes system simulation generation, and today is shifting to continuous evolution of the types of models we use and what simulations these types of models are most useful for. This brings me to model fidelity. There are many types of simplified models, and I'm going to talk about a few today that cover a majority of our use cases. The first and simplest type we call the skeleton model. Skeleton model contains no logic or functionality, but it defines the signals, inputs, and outputs. The next level of fidelity we call the behavioral model. The idea of a behavioral model is to capture the behavior and use cases in a descriptive and understandable way that tries to steer clear of implementation details whenever possible. Building from a behavioral model is what we call the requirement model. Some of you may recall past presentations I've given at Mac promoting the benefits of building requirement models early and often to validate designs before you generate your code. This holds true now more than ever, and we recognize it as an important milestone in our modeling landscape. Last but not least, we have the implementation model. As these models represent the true production code, they can be monsters, not only to deliver, but also to test and simulate. Large collections of these can easily take 20 to 30 minutes to compile and usually don't simulate at real-time speeds. Since they are the highest fidelity, implementation models tend to be the deliverable that most development teams mistakenly emphasize as being the answer to all their problems. This leads me to what I call the implementation model cliff. As I've depicted here, everyone agrees to deliver the implementation model at a milestone when the software will be quote unquote ready. In theory, this is a great idea. In reality, what we end up with is what I call the implementation model cliff, where nothing gets done for months and months and months, and then everyone expects the implementation model to be delivered on time without any bugs and to plug into their system simulation environment without any issues so they can all run their software testing at once. Those who've lived it know that in reality what happens is the model is delivered late, it's full of bugs, and no one knows how to plug it into their own simulation. After the 6 months or so it takes to figure all of this out, it's far too late to help or even test any of the software, and we fall back on vehicle and hill testing to save the day. To prevent this cliff, we instead pursue a graduated stair-step path, which involves starting with simplified models and gradually improves fidelity so that by the time we get to the implementation model cliff, it's just another step in the development path. This approach ensures you have a library of models to always fall back upon and keep progress moving. This becomes increasingly helpful when we go to Hill, where one Hill component is under test while the rest of the components may only need a lower fidelity representation of the design. In this way, we can achieve continuous modeling integration throughout the development cycle. Speaking of Hill, the last thing I want to leave you with is an exciting new capability we have that I call Fast to Go that is powered by SpeedGoat. No, not this kind of SpeedGoat, although happy the skateboarding goat did make the Guinness Book of World Records. Rather, working with several of the math workers, we've developed a quick-click solution to offload heavy and slow implementation models to the SpeedGoat real-time hardware platform. With one click, I can offload my component model to a SpeedGoat model that is ready to deploy. And with a second click, I can deploy it to a SpeedGoat hardware for standalone real-time testing. This is extremely useful for hill stands and breadboards, which may require some heavy implementation models that take dozens of minutes to compile and run slower than real-time, which really compromises their effective usage on a hill. Instead, I can deploy these models to a SpeedGoat, which will run guaranteed real-time and eliminate compile time delays from simulation. It's very fun. And now I'll return it to Robert so he can provide some closing statements on FAST.
Thank you, Nate. And now I will give you a small summary about the presentation you just saw. So the FAST toolchain, as we said, is developed in a collaborative, modern, inner source and agile vision, together with the Networks team. So we really see them as part of our team. They really support us in all different ways. But I think also with the stairs Nate just showed, it helps to detect system issues throughout the development, not only at the end when it's too late. I think the presentation of Raghu and Steven shows that reduced virtual vehicle build time is really now back to minutes instead of months it was previously when we did it by hand. I think the automation process really eliminates modeling mistakes. In combination with continuous integration, we are able to speed up modeling and simulation to an enterprise level. The challenges of all models are wrong, but some of them are useful, will stay. It will not be gone. But the solution with plug-and-play component models are a critical key to success. That comes to the final statement. The FAST doesn't solve all the issues, but it makes the daily life of an engineer more effective and enabled cross-organizational collaboration. And I think that's the power of FAST. And that being said, we are just 5 of us presenting here, but we are not alone. I want to give a special thank to the entire FAST team because it's, as we said, all developers are users, all users are developers. So only the power of collaboration we could achieve this. And that brings the presentation to an end, and I want to thank you all.